everyone hear me okay? Yes. Okay, hi everyone. My name is Tarraneh Eftekhari and I'm based at Northwestern University. And today I want to talk about some ongoing efforts to open some new windows into the transient sky at both radio and millimeter wavelengths. So I'll talk about what we can learn from late time radio observations of supernovae. I'll spend a little bit of time talking about next generation CMB surveys and what we can learn about millimeter transients from those. And finally, I'll briefly talk about fast radio bursts and some prospects for uncovering their elusive origin. Okay, so starting with a little bit of background. When it comes to supernovae, there are a few different aspects of these events that we can probe from radio observations. So we can study the properties of their outflows and the environments that they expand into. But then we can also probe their central engines, right? What's powering these events. And these are typically obscured in the optical and UV. And so if we want to understand the properties of the black holes or neutron stars that form out of these explosions, one way to do that is with radio observations. And it turns out that a lot of this science is really in the domain of late time studies. So for example, at early times, the supernova ejecta is optically thick to synchrotron emission from a compact object remnant. So if you have some kind of ionized wind from a pulsar or a magnetar, this emission can't yet penetrate through the ejecta at early times. And then similarly, if we observe these events early in their evolution, the supernova shock front hasn't yet had time to travel very far out from the explosion site. And so what that means is we're really just probing the material in the immediate vicinity around the explosion, and hence really just sensitive to matter that was ejected from the progenitor in the years prior to its explosion. So finally, we do expect that some fraction of these events should power relativistic jets, but most of these jets will be pointed off axis relative to our line of sight. And so if we point our telescopes at them at early times, the jet hasn't yet had enough time to decelerate and spread into our line of sight. So if instead we wait to observe these events anywhere from 5 years to even 100 years after the fact, the supernova ejecta is now optically thick to any emission from a central engine. A relativistic jet has had time to sort of spread laterally into our line of sight. And then finally, the shock front has now traveled much further out from the progenitor. And so we're now probing matter that was ejected from the star in the centuries before it exploded. And so there's really a whole host of interesting science that this opens up to us. And I'll just focus on 2 topics in particular. And I just want to emphasize that this sort of late time region of the radio transient phase space has really not been explored in a lot of detail to date. So here I'm showing the radio luminosities for various types of radio transients. And you can see that really most extend out to about a few years. In a handful of cases, we've tracked the evolution of supernovae out to about a decade. But beyond that, so pushing to much later timescales, as well as lower luminosities, this parameter space hasn't really been explored in much detail. And so this is really the region that I'm interested in studying, and I'll just highlight some of the projects that we've been doing to sort of push into that new region of the parameter space. So a few years ago, we conducted a large radio survey of type 1 superluminous supernovae using the VLA and ALMA. There's this open question for superluminous supernovae regarding their power sources, right? This question of what is it that's driving these very luminous supernovae? And then separate from their central engines, we're also interested in this possible connection between superluminous supernovae and fast radio bursts. And so that was really the motivation for this work. So this work led to the first detection of a radio source coincident with a superluminous supernovae. This is an event at about 8 years post-explosion. So again, really talking about much later timescales here. And this is really exciting because we do think we're seeing direct evidence for central engine powered emission from one of these events, effectively for the first time. And what we show is that one can reconcile the properties of the radio source, so the time scale and the luminosity, with a model in which it is powered by either a magnetar nebulae or a relativistic jet, both of which would point to this kind of central engine picture. So we've since obtained multi-wavelength follow-up data for this source, really spanning radio to X-rays. And in addition, we also have about 15 hours of Arecibo time to search directly for fast radio bursts from the source. And in this case, the detection would be really cool. It'd basically be the first time that we detect an FRB from a known transient. So that analysis is ongoing. But what I will say today is from our VLA observations, we do see some evidence of short timescale variability, which you can see in the bottom panel here. So we see that the flux density of the source is basically jumping around from epoch to epoch, and the shape of the SED is changing. And we think what we're seeing here is evidence for scintillation from a compact object. So again, this would be consistent with a magnetar origin. And yeah, we're still working on that analysis, but happy to say more if there's any questions. Okay, so that is superluminous supernovae. And again, late times there because you want to probe the central engine. But there's another reason why this late time phase space is so interesting. And that's in the context of type 2 supernovae. So here we see this wide diversity in the different types of type 2 supernovae. And this is telling us something about the processes driving mass loss from these stars, right? So something about the evolution, the final stages of evolution in these stars. And we want to understand, what might be driving that diversity. So we are conducting a systematic search for late time radio emission from a sample of about 300 type 2 supernovae. And the volume limited nature of this sample also means that we're obtaining some of the deepest radio limits on supernovae to date. So these are just a few teasers of some of the radio detections in our sample, where we are detecting radio emission on timescales of about 15 to 20 years after the supernovae happened. And again, here with these observations, we can start to constrain the density profile around these events on some of the largest physical scales studied to date. Okay, so that is radio transients in the centimeter regime. I want to say a few things about how next generation CMB surveys can open a new window into the transient sky at millimeter wavelengths. So we already know from targeted follow-up observations of millimeter transients that there's really kind of a wide diversity of events. They span many orders of magnitude in luminosity. But when we compare this landscape to the radio regime, I think it's pretty clear that we've only sort of just begun to scratch the surface, right? And in many ways, we've been pretty limited in terms of technological capabilities in the millimeter, so both in terms of response times and also sensitivity. So this is where next generation CMB surveys can really sort of change the game here. So these surveys will improve drastically on the previous generation of surveys in terms of not only their sensitivity, but also their cadence. And this turns out to be really critical for these transient studies. And in fact, this was identified as one of the key science initiatives by the Astro 2020 Decadal. And so motivated by this new phase space, last year we endeavored to effectively constrain what the detection landscape will look like with these new CMB surveys. So here we just run a number of simulations taking into account basically the light curves of expected millimeter transients, so both theoretical and empirical. And then for each survey design, so given a cadence, sensitivity, sky coverage, et cetera, we can predict how many events these surveys will find. And what we find is that detection rates will be dominated by long duration gamma ray bursts. So we do expect these things to be detected in really large numbers. And we'll see a small number of some other events, as well as short GRBs with sort of next generation CMB experiments. And that has really interesting implications for multi-messenger astrophysics. and because I'm running out of time, I will just skip ahead to the last thing I want to talk about, which are fast radio bursts. So now we're talking about extremely short duration radio transients. The first FRB was discovered in 2007, so this is a really sort of new field in astrophysics. But it wasn't until 2017 that the first event would be precisely localized on the sky and pinpointed to a host galaxy. Right. That being said, we still don't really know what it is that produces FRBs. And when we look at the pulse properties alone, we see this wide diversity in properties, including an energy scale that spans many orders of magnitude. And so this has kind of presented a challenge in terms of reconciling possible FRB progenitors. But then in the last 6 years, we've seen a growing number of events localized to their host galaxies. So today there's about 30 FRBs that have host galaxies identified. And what we see is that FRB hosts sort of span the entire distribution of field galaxies, right? Ranging from low luminosity dwarf galaxies to more massive galaxies. And so the question then becomes, how can we connect the properties of FRB hosts, their sort of global environments, as well as their more local environments, to FRB progenitors? And that is the main motivation behind the Fast and Fortunate for FRB follow-up collaboration. So F4 partners with a number of FRB discovery experiments to conduct follow-up of well-localized events. And the way this works is that these experiments will typically localize an FRB to within a few arcsecond precision, and then we'll trigger sort of a whole suite of observatories to do follow-up. And this is not only to identify the host galaxy and obtain a redshift, but also to search for multi-wavelength counterparts. Because again, we're after this question of what is it that is producing FRBs. And thanks to the tremendous efforts of telescopes like CHIME, which we'll hear more about in Calvin's talk shortly, we're now moving into this new era where we'll be talking about hundreds of FRB host galaxies, right? So going from 30 to a sample of many hundreds. And so for the first time, we'll be able to build up a statistically meaningful sample of events in order to not only get at this question of, what is it that's producing FRBs, but this will also enable some really nice high precision cosmology studies. So we're very excited about that. And with that, I'm out of time. So I'll just say that there's a lot of really exciting science to be done when it comes to radio transients. If anyone is interested in collaborating, please let me know, and happy to take questions.
I was wondering about the CMD surveys. If you could talk a little bit more about that. What is the cadence?
Yeah, that's a great question. So the one CMD survey of special interest is CMD S4, and that'll have a daily cadence. Most of them will have about a daily cadence. I believe SPT will have has a cadence of about 12 hours.
Hey, Charlie, great talk. I had a question about the scintillating compact source. I was wondering if the situation constraint how big the source is, and whether you can comment on that.
Yeah, that's a great question. And yes, it can be used to constrain the size of the source. That analysis has not yet been done, but that'll be the best kind of idea there. So we're hoping that that'll, place some nice constraints on whether it could be a nebulae, for example.
Great, thank you.
Right, full time, yeah. Thanks, Tarraneh. Let's give another round of applause. And we've been talking about the transient and influence gap.
Right. Am I audible?
Yeah.
Good. Okay, perfect. So thank you very much for to the organizers for organizing this. This is my third year on the fellowship. And I think one of the most amazing parts of it is that it allows you to be independent and sort of do crazy things, which are otherwise hard to do. And I want to show you some of the fruits of doing crazy things with this one particular data set that I like, which is WISE, which is a space mission, but it was funded for solar system objects. But there's so much rich astrophysics that you can do with this data set, especially in the time domain. And what that is telling us about how stars and black holes grow over time. All right. So I'll start with a very iconic picture. This is probably what you show in outreach talks and stuff, which is a nearby galaxy. The things that stick out immediately are, of course, stars. That's what the luminous matter, all the blue stuff and all the red stuff. And in the centers of most of these galaxies, we think there is a supermassive black hole that controls the growth of the galaxy and controls the growth of the entire ecosystem of galaxies. So one of the fundamental questions you can ask in astrophysics then is, how do these stars and supermassive black holes grow over the age of the universe? And the canonical answer for since all of astrophysics has been that stars form from the collapse of molecular cloud cores. You have these dense gas regions which eventually collapse, and you have a gas cloud that starts nuclear fusion, and you get a luminous ball of gas. In a rather similar picture, most of the supermassive black holes, the mass that you have in supermassive black holes, we think comes from these active accretion phases when they appear as active galactic nuclei. They become very luminous. And that's what over time builds up the mass in supermassive black holes. But of course, that's not the subject of this talk. And that's because over the last few years, what we've realized is that there are these somewhat interesting time domain phenomena that appear to be contributing quite significantly to these processes. And that's what I'm going to focus on, and how the WISE dataset has helped us answer those questions. So most of this talk is going to be about WISE. So I want to do a brief technical introduction about what WISE is. So as many of you would know, WISE is a space mission. So it's been orbiting the Earth in sort of this fashion. And what you see is that as it goes around the Earth, it creates maps of the sky. It actually scans the entire sky. And every 6 months or so, you get one single infrared observation of every single part of the sky. And what you can do over the course of many years is that you can stack these images and create very deep infrared maps. That's what WISE has been really spectacular for. But what we've been doing is sort of a different thing. You don't add the images, but you subtract them. And what that allows you to do is to essentially look for things that are changing in those images. Here is an example of how that works. You start with, let's say, an image that was taken last year. On the left, you subtract off a template image that was taken a decade ago, and you see that something sticks out. And those are the kinds of transient point sources that we are interested in. And those are the ones we've been following up. We have a sample of about 15 million sources that we've tried to make sense of. And of course, all of this stuff is hard because these are infrared transients. These are not easy to study from the ground. So it's really been a large team effort to get as much follow-up as we can, all the way from the ground, which is in the near infrared, which you can do from the ground, and even going to radio wavelengths and X-ray wavelengths to get as much information as we can. I know many of you in this room will be on the tags or already on the tags for these telescopes. So please be kind to us when you hear about infrared outbursts in WISE. All right. So now the fun part, the science. So what this data set in particular, I want to focus on two specific questions that this data set has allowed us to address. The first is how stellar populations might be altered through mergers. As stars grow and evolve, they merge into each other, and how that might be changing populations. So in case you're not familiar with stellar mergers, the idea of a stellar merger is that you have two stars that were essentially born together. And at some point, one of the stars is evolving off the main sequence, and then it engulfs its companion as the two come into each other. And when that happens, what we know happens is that it powers a very luminous outburst. What you see here is an actual Hubble time-lapse image of a galactic stellar merger. What you see here is the light echo of the dust that surrounded the merger. But what I really wanted to focus on is that as time evolves, the central merger event itself becomes very red. It becomes almost completely dominated by infrared emission. And that's because this outflow from the merger is actually producing molecules and dust that is obscuring the optical emission, but making it very bright and long-lived in the infrared, making them almost purely infrared phenomena, if you will. So these events we think happen about once every few years in the Milky Way, and we can find a few of them every year in extragalactic systems, thanks to these optical time domain surveys today. But what I wanted to focus on is really that even though stellar mergers sound like a curiosity, they're not really just a curiosity. And that's because if you look at the HR diagrams of young star clusters, what you see is that the entire diagram sort of splits into multiple sequences. And what has been shown recently is that you have this sequence of stars that we think are normal stars that form through normal star formation. And there's a sequence of blue stars that appear to be peculiar in their chemical properties, rotation, colors, that all seem to be consistent with them forming out of mergers. And and that's been confirmed if you just look at the mass function of stars in these clusters as well. The normal stars follow the canonical salpeter IMF, whereas the peculiar stars, the merger products, have a mass function that is much flatter, and that is what you would expect from mergers. So, and to me, that's really a profound statement to say, which is to say that if you looked out there in the star cluster today at night, a third of those stars underwent mergers during their lifetime. So it's not just, just another curiosity that is happening. It's not just another transient. These are fundamentally changing stars in the universe. So, of course, when we started looking at this problem, saying that, hey, what do we know about stellar mergers in the universe? And what turns out that, so what I did was, here are the progenitor masses of all stellar mergers that have been discovered in optical surface. And if you look at the x-axis, you'll see that there is this preponderance of extremely high mass stars. Most of the things we know of are like 8, 10, 20 solar masses. And that's kind of curious, right? Because we know that this mass function tells us there are many, many more lower mass stars than higher mass stars. So why do we not see any of the lower mass stars merging? We only see the higher mass stars merging. So with this, I started a project with Morgan McLeod, who's a postdoc at the CFA over here. And what we speculated at the time was that maybe the lower mass mergers, which evolved to these very large red giant phases, by the time the merger actually happens, they self-obscure themselves in dust. And a way to imagine that is that if you look at the animation over here, as the two stars do this dance around each other towards the end of the binary itself, they tend to expel mass from the system, and that might be producing a lot of dust. And we showed that especially lower mass stars would undergo huge amounts of obscuration as they went up the red giant branch in this diagram. So what we've been doing is that with this follow-up program, we've been systematically looking for infrared outbursts with observational signatures that are consistent with stellar mergers. And it turns out, yes, there are this population of infrared-dominated stellar mergers that we've identified. I'm showing here 3 examples. One is in the galactic plane. It's a stellar merger in a own galaxy that has almost no optical emission. The next one is in M31, right next door. Again, very faint in the optical, but super bright in the infrared. Another one is in a galaxy about 5 megaparsecs away. The common theme of all of these things, and I'm showing the Ys in black and yellow, and the optical light curves. The common theme in all of these is that the infrared emission is super luminous. It's bright, some of the brightest infrared transients in the local universe. The optical emission is usually a factor of 100 to 1,000 fainter. So these are purely infrared-dominated transients. They look like stellar mergers, and they all appear to be coming from the low-mass progenitors that have been systematically overlooked in these optical searches for stellar mergers. All right. So in the last few minutes, I just want to focus on the next question that I highlighted at the start, which is what can we learn about the growth of black holes from infrared observations like these? So obviously the canonical picture has been that black holes form because of these supermassive black holes form because of these active galactic nuclei phase. But a particularly interesting way to form supermassive black holes is actually through tidal captures. So in case you're not familiar, we know that these events happen in the universe. These are tidal disruption events where you have a star that ventures too close to a supermassive black hole, and it gets ripped apart, producing this luminous electromagnetic emission that we can see in optical and X-ray surveys. And there was a particularly interesting paper a few years ago, which I like because the first line of the paper says, can star captures account for the growth of the largest supermassive black holes? No. But can it account for the growth of the lightest supermassive black holes? And the answer is yes. And a simple way to think of that is that every time a star gets disrupted by a black hole, which you think is about 1 every 10,000 years in a galaxy, it accretes about a fraction of a solar mass. And over a Hubble time, that is enough to produce like a 10 to the 5, 10 to the 6 solar mass black hole. But the biggest uncertainty in this statement is, of course, what is the rate of tidal disruption events, which is very poorly constrained. And part of the reason is that these are really happening in some of the most dustiest regions in the universe, right in the centers of galaxies. So the question that we wanted to ask is, can we find these extremely dust-obscured events unbiased by the foreground dust that is surrounding these supermassive black holes? And turns out that a particularly interesting way of doing that is because I didn't know the audio, sorry. Okay, anyway, so what you see here is that, yeah, it doesn't work. So what you see here is that as the TDE happens, there is a dust echo that is propagating through the. That was not intentional. But it kind of proves the point. Yes, so you have a dust echo that is shining around the black hole because of the electromagnetic emission. And you can actually search for TDEs using these dust echoes themselves. And that's what we've been doing in the mid-infrared. So what we did earlier last year is I've been working with postdoc Christos and grad student Megan at MIT. What we've been doing is that we're looking in the WISE dataset for these luminous mid-infrared flares in the centers of galaxies. Here is an example of what we believe is the nearest tidal disruption event that has ever been discovered. It's only 40 megaparsecs away, has no optical emission as far as we can tell. It's just a luminous mid-infrared flare that happened somewhere in 2014, was overlooked for a decade because no one was looking in WISE. But once you start looking at the data, it's the most obvious transient you can find. And what we've now converged on is the sample of TDEs that are purely in the mid-infrared, all within the local universe, 200 megaparsecs. They're all being overlooked by optical and X-ray surveys. And this entire sample, what that really allows you to do for the first time is get an unbiased rate estimate for infrared TDEs in the local universe. This is what Megan has been working on. Here's a luminosity function of TDEs in the infrared bands. What you see is that the rate is very comparable to optical and X-ray searches. And what that tells us is that we've basically been missing a third of the TDEs in the universe because you're not looking in the infrared. And once you combine the rate of TDEs in the infrared with our approved JWST program, which will be observing some of these TDEs in cycle 2, what we aim to do is that get the total amount of energy radiated in these TDEs that allows us to essentially estimate how much mass is accreted into black holes because of these infrared events. Thank you. So I'll quickly summarize. We do have normal stuff happening as well in case you're interested in young stars and stuff. I have a student, Vin, who's been working with Professor Hillenbrand at Caltech looking at young star outbursts. Professor Christina Eiler's group at MIT is looking at quasar structure functions in WISE, which is a good way to study supermassive black holes. And if you have an idea, we are planning to release this dataset very soon, so please get in touch with us. Thank you.
Very nice talk, Kishalay. I have two quick questions. So when you're discovering these purely mid-infrared transients that are like mergers from low mass stars, were you getting anything special in the spectra? If you were getting any spectra that differs from the mergers that you usually observe in the galaxy? And the second question is that these are, I believe, are expected to be more common than the merger of higher mass stars. Do you think with LSST in the future might be able to come up with a rate for how often these happen? Because probably the case is different than WISE. I'm not sure if you might be able to do that as WISE. You can tell us. But would LSST be more useful for that? Thank you.
Right. Thank you. So yes. So for the first question, I think the most difficult part about following these up is that these appear to have no optical emission at all by the time we find them, because WISE only gives us 6-month cadence data, which is, so we only find them, let's say, a year after the outburst. And by the time they're already obscured by dust. So we have to go to like 10-meter class telescopes to follow up something discovered by a 30-centimeter telescope. So that's one of the main challenges. They get obscured by dust very soon. And about the second question, I think the thing that is unique about these stellar mergers is that they redden very quickly. The colors change very quickly. So I'm really hopeful that with the multicolor coverage that LSST provides, it will be very easy to identify these things, even with the whatever 2-week cadence, because these are very slow events inherently. So I think that there's a lot of hope for that.
It's the range. You're too far away from the.
Okay. Nice talk. You said at the beginning 30% of smart birds. Is that what you said? Is that including the infrared ones that will start detecting now, or does that increase the rate?
So I think the 30% is based on the study of stellar populations, not from the transient side.
Okay.
So based on the stellar populations, 30% of stars look like they have undergone mergers at some point in their life. Yes, but it really is like for massive stars, probably all of them undergo mergers at some time in their life. For low mass stars, I think probably goes down to maybe 10-15%.
So this would affect the supernova rates?
This would produce a lot of weird supernovae, I think. The ones that were not supposed to go supernovae, but eventually became massive enough to go supernovae. Yes, those phenomena would exist.
I want to stop.
Yes.
Okay, time is up. We can ask Kishalay questions later. Let's give you another round of applause. That's the Leung, talk about China servers.
All right, thanks for the introduction. Oh, can everyone hear me?
Higher.
Yeah. Is that better? Yes, okay. Hi, everyone. As Ricardo said, my name is Calvin, and today I'm going to be talking about fast radio bursts as observed with Time FRB and its new campaign to build outriggers. And so Tarraneh earlier gave us a nice introduction really quickly to fast radio bursts. I will be expanding on that in more detail so that as a sort of a general overview of the field and what you can expect from it as someone who studies contact objects, someone who studies cosmology or does radio instrumentation in the next 5 years or so. So as a reminder, fast radio bursts are bright, brief, and typically non-repeating radio transients. They have the brightness of about your pretty bright radio galaxy, about a Jansky, and they're really hard to observe because they're both so brief. And since they're non-repeating, you can't even slew a telescope to go catch one. We know that they're extragalactic in origin, and we think that the leading theories for these bursts are that they come from magnetars. And as Tarraneh alluded to earlier, they're extremely common. In fact, over the course of this talk, which hopefully does not run too long, we expect to see 3 or 4 fast radio bursts. One happens every 2 to 3 minutes. It will be observing everywhere on the sky. So these are really everywhere, just waiting to be found by our telescopes. And we're just beginning to scratch the surface of the fast radio burst sky. One of the most salient features of fast radio bursts and the most powerful is this feature called dispersion. I've shown a dynamic spectrum of fast radio bursts. On the right, you can see time on the x-axis and frequency on the y-axis. And you can see that the red photons come in later than the blue photons. This is a very precisely measured time delay. And the reason for this is because red light travels slower in the plasma. And only after we correct for this characteristic dispersion chirp, it's like a gravitational wave chirp, but backwards, do you recover something that looks like an impulsive millisecond duration radio transient, as I promised earlier. So this is the contact object side of fast radio bursts. Today, I'm going to be talking about something totally different and its connection to fast radio bursts. This is a sequence of snapshots from the illustrious TMG simulations. You might wonder what connection this has to fast radio bursts, but you can see that if we just look at this simulation, the top and the bottom panels illustrate the same halo as seen in different generations of this illustrious series of simulations. And you can see that the gas properties surrounding this halo are very different as you see it in density, temperature, and metallicity. In fact, if I didn't tell you that these were evolved from the same initial conditions, you might not believe that they indeed were generated that way. And so this points to, you can see like all this rich structure, it points to not only the complexity of the simulation, but also how much more we had to learn about the distribution of baryons within and surrounding these galaxies. And this is where fast radio bursts come. That fast radio dispersion I mentioned earlier turns out to be an excellent probe of this gas. So as I mentioned earlier, FRBs are generated as these millisecond duration transients. They pass through some electron column and come to us as this dispersed chirp. And we can measure this dispersion extremely precisely. It turns out to just be an integral of the electron column density along the line of sight, making this an extremely powerful probe of baryons. And it's very complementary to existing probes, such as the Sunyaev-Zelgovich effect, because it measures some different line of sight integral. Some really cool properties of dispersion is that it's completely temperature independent. It's good up to 10 to the 10 Kelvin, and there's no like systematic, there's no funky weighting along the line of sight. And it's also completely insensitive to the metallicity. So if you want to understand the density, temperature, metallicity properties of your gas, you probably want a couple of independent probes, and dispersion adds a particularly clean one to the mix. So we want to catch a lot of these fast radio bursts to use them as the next great probe of cosmology. And the way to catch fast radio bursts has sort of been trailblazed by the telescope collaboration I work with, CHIME. This is my t-shirt. CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment. And as its name suggests, it was initially designed as a 21 centimeter machine. It observed over a frequency range of 400 to 800 megahertz, it's sub-gigahertz, so it was lower than the VLA, lower than the VLBA, higher than LOFAR. And I guess from this cover of Nature or from my background, you can sort of barely see, you might try to guess, well, how big is this radio telescope you're using? Is this like some massive machine? Some guesses I've heard in the past are at times like 100 meters large, 20 meters large. Also, some people guess like 3 meters large. And it turns out that all these answers are correct. We have the sensitivity of a 100-meter dish. Each of these 4 cylinders, which time is comprised of, is about 20 meters wide and 100 meters long. There's 4 of them. And we have this field of view of a 3-meter dish. And this is extremely cool because for a 3-meter dish, your lambda over d is really large. So you have 200 square degrees over which to survey the sky for fast radio bursts, but with a collecting area of a 100-meter dish. So you get the best of both worlds by breaking up your aperture into these funky cylinders. Of course, that 200-degree field of view is not uniform on the sky. We have this barcode-shaped field of view, and once every night we survey this sky for fast radio bursts. It's approximately equivalent to having a bunch of GBTs, like all pointing in different directions, simultaneously searching for fast radio bursts. And this strategy has enabled us to catch fast radio bursts faster than the rest of the world combined. This is our first catalog, whereas everyone else in the world, from the time the first fast radio burst was discovered until 2018, discovered about 50 of these events. In our first catalog, we dropped 500 of these guys with just a year of data. And now it's 2023, we observe 24/7, and you can guess how many fast radio bursts we have at the moment. So what's the catch to this awesome machine? Because we were originally designed as a 21-centimeter experiment, we don't have angular resolution. So we have all these bursts, but we don't know where they're coming from. Our astrometric precision is about an arc minute, which does not let you find the host galaxy of that fast radio burst, as Tarraneh briefly alluded to. Here's a picture of the Hubble deep field. Really cool, but for us, it means that like within arc minute circle, there are hundreds of these host galaxies that we don't know how luminous this burst is or have any information about its possible progenitors until we have angular resolution to localize these things. In fact, the Astro 2020 decadal suggests that we do time, but with arc-second localization capabilities, so that we can pinpoint the host galaxies of these bursts. And that's exactly what we've been trying to do for my PhD. I worked with 2 close collaborators, one in Canada and one in Green Bank. We built these little outrigger telescopes, and we use them to pinpoint a fast radio burst at the time of detection. So at the time that Chime detects one of these guys, we tell our friends, and they're buffering data, and they save it to disk. We correlate the voltages offline, and we pinpoint a fast radio burst to its host galaxy here. We also take some spatially resolved spectra. We find star formation as traced by H alpha. That tells you there's some massive stars in the vicinity of the fast radio burst, which is sort of consistent with this magnetar origin. This has been really cool. We've been expanding this to this operation, scaling it up from these little dishes. I'm going to skip over this stuff because I'm running out of time. But basically, for this burst, you can sort of start to probe baryons along the line of sight. We measure 500 units of dispersion, and you can subtract off all the stuff you can model, the Milky Way's ISM, the Milky Way's halo, stuff into IGM, and what you get is that a first glimpse into the IGM of the host galaxy of a fast radio burst. So we're scaling up our operations to 3-cylinder telescopes, in contrast to those humble little dishes that I was talking about earlier. These are outriggers that are going to be built Green Bank, Hat Creek, and also this other one called Allenby, which is very close to Chime. We actually have a different name for that now. The name for that one that I'm showing at the top here is KKO. This name was given to us by the Upper Similkameen Indian band, with whom we maintain very good relations. And you can see that we're sort of in the process of building some of these guys. KKO is up, Green Bank is almost up, Hat Creek is basically a flat field. And here are all the folks who have been working really, really hard to get these outriggers on the sky. And so my NHFP project is going to be commissioning the third and final outrigger so that we can localize these things in the north-south as well as the east-west directions, giving us a unique view into their origins. It turns out the calibration for this this new VLBI array is super hard because no one does VLBI at sub-gigahertz frequencies. LOFAR does a bit, but they don't have great astrometric precision. And so we need to basically roll our own set of astrometric calibrators, which Alice and Shion have been really taking the lead on doing. Here's our third Outrigger site. You can see the Allen telescope array there already, but we're still waiting on the environmental permit to pour concrete and put steel pillars in the ground. Now I'm going to spend the last 2 minutes talking a little bit about the more exciting applications of FRBs we have once we detect and localize hundreds or thousands of these things. So one of the most basic cosmology questions you can answer is, what is the redshift dispersion relation? Things are farther, higher redshift, they should be dispersed more. And in a universe where the IGN is totally homogeneous, you'd expect this to be a pretty tight scatter. Of course, we don't live in a homogeneous universe, thankfully. So we expect some more scatter. And we can start to probe this with many dispersion measurements as a function of redshift, which you only can get from these localized fast radio bursts. I'm going to quickly flash through some other opportunities. Please talk to me if you're interested in these sorts of things. I think a lot about these, but we haven't been able to do them yet just because we haven't gotten the telescopes on the sky. So sort of one of the most exciting science cases is to understand the origin of FRBs. We can pinpoint the most nearby events and look at that star that hosts the FRB. Maybe it has a binary companion. We can look at the FRB luminosity function, their host galaxies, and maybe even peer into immediate host environments. In a far off future where we have thousands of these things, we can start to make dispersion measure maps of the sky and start doing a program of angular large-scale structure correlations, which we've already started with in China. We can look for microlens or nanolensed FRBs, which is a topic that's very near and dear to my heart. And we can also make that DN redshift Hubble diagram, which I sort of alluded to earlier. We can also look for strongly lensed FRBs. So in summary, the future of FRB cosmology is very bright. It consists of both studies of baryons and gravitational lensing in our very exciting universe. At this point, I'll say thank you to everyone for being here. Thanks for all the collaborators who are working on Chime and Chime Outriggers. And now I'll take any questions.
Can you do rotation measure?
Yeah. So that's something I totally skipped over, but you can measure the polarization angle versus frequency and unwrap that to get rotation measure.
Yeah, I'm not an expert galactic person, so it's maybe a naive question, but so in order to use the dispersion of FRBs to sample or understand intergalactic medium, do you have to make the assumption that all FRBs originate with a certain degree of non-dispersion in the same way? And how big of an assumption is that?
Yeah, so these, the FRBs themselves are like a millisecond in duration. And in comparison, the dispersive sweeps are like tens of seconds long. So you really have a very well-defined dispersion measure for these events. And small differences are like order of like 0.1%. Great question though.
Hi, very nice talk. How do you detect strongly lensed FRBs?
That's a great question. We should talk about it afterwards. It's really hard because you have this transiting telescope which never surveys the same plane twice.
We have time for one more question. Oh, I didn't see something.
Really sorry.
Brilliant, Scott Cohen. My question is just on the cosmology side, what do you think is the nearest prospect that we can achieve?
Yeah, I think we can start to probe like the CGM and in particular understand what that means, or what sort of models of galactic feedback are allowed or ruled out by the presence or absence of baryons.
Yeah, good. Let's move on. Let's thank Calvin again. There's an email about the discovery of a briefly imaged type 1 expert.
You mean like, no? It is not. Good. No, does that work? People in the back? Yeah. Success. Can you hear me in the back with this? Okay. Great. Thanks a lot. That was actually a good segue with the strong lensing at the end. So I'm glad about that. I'm a first-year Einstein Fellow at the Space Telescope Science Institute. as part of the Transient Science and Space Telescope group. We have a fancy logo, so you know we're legit. And today I'm going to talk about this triple image type 1a supernova at redshift 1.8. So we got a little bit of background on this on Monday. That was 2 days ago. I assume everyone forgot everything. So I'm just going to review quickly to motivate this. So I'm not really going to go into this since we talked about it, but just a reminder of the Hubble constant tension, 5 sigma tension between this early universe, Planck inference using lambda CDM, and the local distance ladder measurement using type 1a supernovae. So one major issue in cosmology that I'm going to address here. And then mysteries of dark energy. So in this context, what I mean by this is that here on the left, we've got constraints from type 1a supernovae in red and C and B VAO in yellow and blue. This is on the y-axis, the dark energy equation of state, assuming no redshift evolution. In that case, we actually have decent constraints. But if you relax that assumption on the right, the y-axis is allowing for just the simplest form of redshift evolution. That degrades pretty quickly. So in terms of these two pretty significant questions for cosmology, the H-naught tension solution could be new physics, it could be unknown systematics. At this point, it's a bit of an impasse on that. And so, as Anwar mentioned on Monday, one of the best ways to help resolve this at this point is to add new measurements with unique probes to see where they fall. On the nature of dark energy side, we basically need more data over a wide redshift range, and we need complementary probes. And by that, I mean more things like this, where the CMB and type 1a supernovae don't constrain these parameters very well on their own, but together, since they're orthogonal in this parameter space, their combined constraint is very tight. So in terms of the gravitational lensing, someone showed this, I think, exact plot, but I'm just going to review quickly that this can basically be summarized by matter telling space how to curve, and in our case, telling energy then how to move. So in curves around massive objects. And if we bring that to this astrophysical distance scale, we have some bright thing in the background here with light bending around this intervening galaxy, or it could be a cluster of galaxies, as we'll see. And this forms, in this case, 2 images of the background source. And then if the paths of light are different lengths, and if there are differences in gravitational potential along those paths, then the light from this background source will not arrive simultaneously, but instead arrive with some delay between the images. And this delay we call delta t, or the time delay, which was discussed by Anwar on Monday in the context of multiple imaged quasars. He talked about measuring the Hubble constant with this, as well as various systematics that they were trying to overcome. So you're going to bring this to supernovae then and say, well, why do we care about supernovae then? We have type 1a supernovae already measuring cosmology. We have multiple image quasars measuring cosmology. So now why do we need multiple image supernovae measuring cosmology? Well, one, just to clear this right away, even if our multiple image supernovae are 1As, it's still the way that they're measuring cosmology is still completely unique from the type 1a cosmology that we're trying to complement. And so this is still unique from that. And then in terms of relative to quasars, a few possible advantages. One is that they fade quickly, which enables some cool tests that I'm going to mention in a few minutes. Another is that they have pretty simple and predictable light curves usually. So on the right, we have just some model quasar light curves and cartoon supernova light curves, but are relatively realistic in terms of their shape and variability. So this leads to easier observing and easier measurements. And then if your supernova happens to be a 1A as well, then you can leverage the fact that we kind of know its luminosity to help break this match sheet degeneracy that Anwar mentioned on Monday, where they were trying to break with stellar kinematics. So you could do that sort of for free with the supernova itself. It's a 1A. There's some other stuff that I don't have time to get into, but I'm happy to talk about at the end if we are curious. So the first of these multiple image supernovae was discovered in 2014. It was supernova Refstall. This is lensed by a massive cluster, not a galaxy. And the initial discovery was just the 4 images on the bottom. So these yellow point sources on the inset. The 5th image, which is on that top with the lines connecting it, was not visible at the time of the discovery, but the lens model predicted that it should be there. And so this enabled a cool test. They had a series of lens models. They predicted the arrival time and location of this 5th image, waited a year, followed it with Hubble until it appeared, and then we're able to get a cool test of how robust their lens models were as a result. And that's just something you can't do with quasars since they're always there. So getting to this kind of new discovery of this, this is the G165 cluster. This is an HST image. And then this was imaged as part of a JWST GTO program, Pearls, which is observing a variety of clusters. So here's that JWST image, which is a little bit nicer, and I'll zoom out on that here to show the white basically in this cluster is at the cluster redshift, which is about 0.3. And then this banana thing on the right is 3 images of the same host galaxy at redshift 1.8. So the 3 kind of bright points are the individual images of the galaxy. And then there's a small point source, the blue point source that's circled 3 times here, which is 3 images of the same supernova that happens to be going off in that galaxy at the same time that we took this image back in April. So you can see that this host is pretty bright and pretty red, and we don't have the ability to make a difference image for photometry at this point because we haven't observed it yet with JWST while the supernova was not present. So this led to some cool work from Gabriel Camina, who modeled the combined lens and galaxy light in order to subtract it off and create something of a synthetic difference image that we then use to measure properties of the supernova. So you can see here, move this a little bit. You can see here that just by eye, the central image of the supernova, this point source here, is much brighter. This bottom one's a bit fainter, and then you can almost not see the top one by eye, but it is there. That's due to differences in the time delay as well as magnifications. And so I'll show that here. So we measure properties of that, and then there we go. And we just put them on a light curve. So this is one of those things that you have to wrap your head around when doing gravitational lensing, but this is a light curve showing observer frame time and brightness on the y-axis, but all these observations were actually taken here at 6033, and then I shifted them by the model predicted time delay and magnification. So this is basically what you would look at if there was no lensing in the way, and we just happened to take 3 observations spaced by 50 days or so. And then the curves here are a type 1a supernova model at redshift 1.8. And so this is why at the time of it in April, we looked at this and we said, well, we think this is a 1A, it's a good fit. And so we got a director's discretionary program with JWST to follow this and get some near spec data. So this is reduced by Wenlei Chen. And this is, again, one of those things. This is 1 epoch of spectroscopy, but we get a spectrum for each image. So we get 3. And if you're not a 1A person, then this is basically what you look for the 1A, the Silicon 2 line. So this is indeed a 1A, and in fact, it looks like a relatively normal 1A, similar to those that we see in the nearby universe. So now that we know it's a 1A, that's great. We can continue with our light curve modeling. So this was again the model we had, and just as a reminder, we have the 3 images. So basically, the top image is this faintest one, the bottom image is this middle one, and the central image is this brightest one. We got 2 more epochs of data with JWST. So here's what the final light curve looks like. 2 more epochs means a total of 3 with 3 images. So we get 9 light curve points. So separated by these images. So you can see there's 3 of image 2, 3 of image, of image B, 3 of image C, and 3 of image A. The interesting thing here is that this is not a new fit. I just took the model that was a fit to our original data, just these 3 points, and then just plopped our new photometry on top of that, and it seems to be quite good. So what that really tells us is that our lens model predicted time delays and magnifications are probably quite accurate, and also tells us that this is a pretty normal type 1a supernova because our model predicted the photometry almost perfectly. So what are we doing with this now? So the first paper on this is actually out, is just the discovery paper. So the kind of cosmology papers are going to be quite soon. So I have one measuring time delays from this light curve. Wenlei Chen is measuring time delays directly from the spectroscopy, which is quite cool. And then there will be a measurement of the Hubble constant later this fall that uses these values. This will be the second measurement of the Hubble constant with a multi-image supernova, and the first with a type 1a supernova. So a quick look to the future of where we're going with these. So this is a part of an effort of this LensWatch collaboration which Anwar's a member of, and I'm a PI. And we have 15 orbits remaining for if we find another one of these before December. And then we have 3 more triggers, 45 orbits and 8 near-spec hours for ideally to get 3 nicely observed more of these in the next 2 years. And with these, what we're hoping to have is a sample of 5. So Refstall, the one I just showed you, and then 3 more from this new program. And the reason we want 5 is, so 5 statistically is enough to, assuming we agree with one or the other, differentiate between the shoes and Planck values of the Hubble constant. And then also, this is the dark energy equation of states with the redshift evolution plot again. And I'm just showing this because the light blue is now is the same as dark blue, the green is the same as red. And now my red is the sample of 5 lens supernovae. And you can see that this happens to come in at quite a complementary angle, and we can improve the current constraints by about 40%. So that's our plan. And then, of course, if you wait a few years, we should find a whole bunch of these from Roman and Rubin. I'm particularly interested in Roman, so if anyone's excited about that, I'm happy to talk to you more afterwards. And that's it. I'm just going to leave this zoomed out version of the G165 cluster, which is cooler when you're not looking in light and on a projector screen, but you can look at it online later. Thank you. I'll take questions.
Hi, thanks for the talk. So can you talk a bit more about how is it that you're searching these images for these lensed events? Because you usually just get one token.
Yeah,
Yes.
it's a good question. So what we've been doing for not just pearls actually, but kind of in general with public JWST data at Space Telescope all year is doing JWST minus HST subtractions in neighboring filters. So this was discovered in a JWST F150 minus HST F160 image. And so we've been kind of doing that throughout the year, looking for interesting transients.
More questions?
Great talk. I just have a question. Is the single object uncertainty on the H0 similar to the single object uncertainty that was talked about on Monday? And you said you're going to have 7 of them. Will you be able to maybe send this to discriminate between the tension with 7 objects, like significantly?
Right. So it depends a little bit on what type of supernova they are. So the first Hubble constant measurement with supernova Refstall, it ended up being about 6%, partially because the time delay was a year. And the uncertainty that contributes to the Hubble constant is like directly. So if you have like a 1% time delay measurement, that contributes 1%, and then the other part is lens modeling. So that basically means if we find the rest of the ones we find all have long time delays, then we'll have smaller uncertainties on our measurement. If they have short time delays, they'll be relatively high. Additionally, if they're all type 1As, that will be also higher precision and fewer systematics like the matching degeneracy. Individual objects are comparable, I would say, to quasars. And like I said, yeah, so we assumed that we would end up with our whole sample being similar to supernova Refstall. And with that, you need 5 to differentiate at 3 sigma between Planck and shoes. But that does assume that we agree with one of them, right? If it ends up in the middle, it ends up in the middle.
Here's time for one more question. No, thanks, Justin again. And I want to thank the speakers for the session. I think we're done for today. Do you have anything to announce?